Welcome. My name is Emir. In following 25 minutes, give or take, I will present you something different. So I'm not going to present one project, one product, or whatever. I will try to describe you what University Computing Center is doing to... My boss is up there. Is doing to cater for a specific set of users. And in the very end slide, I will provide one really bright slide for the future that is to come. So I hope there will be some questions there. So let's see how this works. So I know that initially I said this will be about the high throughput computing and about the OpenStack and Ceph, but I guess most of you have already tried these things, have heard something about it, so there will be no demo of these particular two projects. I will try to put them in context of what is needed in our particular use case. So I will first try to describe what is our use case, what's the problem that we are solving. Then I will describe two concrete services that we have been running for years now, and how the users are using it, and what were the issues with them, and why we went down the cloud road. Then I'll try to describe what we did in order to build this cloud infrastructure, and finally this describe some of the issues that we've already hit with it, some, as I said, bright future work, and finally try to draw some conclusions. Feel free to stop me at any point if you have some questions. I will try to finish in 25 minutes, so we have at least 5 minutes for questions. So, what are we solving? We are trying to cater for computational scientists. Now, when I started working in the University Computing Center, which is now more than 16 years, there weren't that many of them, but nowadays it's pretty much all of them. What is computational science? So it basically boils down to enabling scientists to utilize vast amount of computational resources, whether it's processing power or storage, in order to solve their complex problems. Of course, this does not envelop the whole science. You have still some scientific areas where you don't need the computers, but to be realistic, most of them are nowadays unable to do any of the proper science if you do not give them reasonable tools from our side. There are three obstacles when we talk about the computational science. So I will not talk about the... I will try to focus on traditional computational science, so I will not go into Google, Facebook, and their problem that they're solved with their massive distributed infrastructure. I will focus on these scientific guys. So for them, there are three obstacles. First obstacle is, of course, the hardware. So you're a bright new physicist. You want to find the Higgs boson. You already built several billion euros worth of a machinery which was producing petabytes of data out for you. First problem that you will hit is where do you analyze all this data? So somebody needs to give you this hardware. You're not gonna succeed with these little boxes that you have in front of you. Second thing is the software. So once somebody gives you hardware, as a bright future Nobel winner, you're probably not into software engineering. So somebody has to provide you with this software. And finally, if you're in the area where the algorithm cannot be parallelized in order to use a vast amount of computing resources that somebody already bought for you, well, you're not a proper computational scientist. So if you're able to jump over these three obstacles, then you're basically reaching at least us or some other big supercomputing center out there. As I said, this pretty much envelops all the scientific areas, so astronomy, chemistry, earth science, life science, biology, blah, 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 a bunch of them, mathematics. And then if we go outside of the scientific community, the finance, you already know that the finance prediction thingies are running on huge clusters. They are not being analyzed in some single boxes where somebody has big Excel sheets and stuff. Engineering, military, if you want to do the scenarios or simulation of big battles, then these things are something that you need. So there are two general areas which are kind of trying to build systems and provide software for these scientists. One is the high performance computing. You've probably heard of the supercomputers, which is something that it gets published. There's a big top 500 list, which gets published every 6 months, and it's always Chinese and Americans trying to push somewhere in front. Unfortunately, Europe hasn't been on the top for a while now. With the supercomputers, it comes basically down to building really specific systems, which enable you to run applications in a using really, really large amount of CPU cores at the same time in order to minimize the runtime. In these systems, everything has to be in one place. So as you can see, the Summit, which is the most powerful machine today, everything is in one big space, and you can basically run jobs that scale up to 10,000 CPU cores. So just remember these numbers, or try to remember them. So 200 petaflops is the peak performance that they achieved, so it's floating point operations per second. And they basically have around 30,000 V100 and Power 9, so it's an IBM thingy. So supercomputers is basically for the big players, so DOE or in Japan, if you have a really big institute that solves some really difficult problems like climate modeling or stuff like that, so they get the supercomputers. The rest of us, we get D clusters. What's a cluster? Cluster is basically, I have a really old picture. So it's just a bunch of PCs, which you can just go and buy pretty much anywhere else. You do an interconnect, as simple as Ethernet, though nowadays clusters are way more complicated, as you will see a bit further down the road. And you use a cloud middleware to provide this bunch of independent computers as a single system to a user. I will come with a similar picture later. Now, if you compare the high performance computing with high throughput computing, which is something which is really hard for us to explain to our users, but it comes down to this. In high performance environment, you try to minimize the runtime, and you do that by spreading your workload over a bunch of resources. In order for that to work, the resources need to be the same, otherwise you will be running as fast as your slowest machine, right? And of course, you need to have low latency, high throughput network in order for them to be able to quickly communicate with each other. As I said, this could be achieved by using a cluster or by using a supercomputer. In HTC, the requirements are lower, which basically brings us to infrastructure which is based on a bunch of small clusters, which do not have high performance network in between of them, because your applications consist of large amount of tasks which are independent, which means that you are aiming for a high capacity of CPUs. You do not care about the individual runtime of your task. You just want to run as many of them as possible. So you, or older of you, will still remember SETI at home. That's an ideal case of an HTC computing. The other example is the LHC, which is that's where the grid word came from, basically. Though it came from US, they were the heaviest users, and they are the heaviest users still. Why? Because they're producing petabytes of data, and their analysis boils down to taking a picture, running a single core process on it, and trying to find a Higgs boson. They already found it, but they're looking for other stuff nowadays. In this category kind of falls the LTOS, the long tail of science. So long tail of science is something that you cannot really fit in HPC. These are a complex workflow where you have a first phase where you need a little bit more CPU, and then you need a little bit more RAM, but then less CPU resources, and then a little bit more of I/O, and then a little bit, and it constantly changes. So you cannot really fit these things nicely on HPC, because the HPC is something which is really expensive, and this is where you really look at the usage of resources, and you do not allow people to run crappy algorithms on. So, to summarize, the HPC versus HTC, HPC is a single resource thing. It sits in one site, while the HTC can be distributed a bunch of clusters. Again, the processors in HPC, you're trying to have the homogeneous environment. You are trying to put as faster things as you can. Of course, add accelerators, and then for bioinfo community, for example, they really like SMPs. So a single machine that has up to 100 cores with the access to terabyte of RAM. They do not like multiple nodes. They do not like distributed memory. They just want shared memory systems so they can run something like OpenMP or pthreads. While on the HTC side, as I said, usually you have just people submitting single core jobs, which for them, you just need to give them a bunch of resources. They do not care if some of them are running slower, because in some cases, and it really happens for us, they kill a bunch of those resources, some are in a bunch of those jobs, some are halfway through because they just need output from some of them in order to conclude something, and then they start a new array. The storage, again, with on the HPC side, you go for the NVMe SSD or some kind of faster HDDs, which are usually on a parallel file system, so that you can push a big throughput there. For example, on our cluster, we see peaks which go up to like 5 gigabytes a second and stuff like that, which is just streaming down on the disks. On the HTC side, as I said, the LHC is a perfect example. So they have a bunch of cheap stuff because for them the capacity is more important than performance. Finally, the network. The HPC side is low latency, high throughput, so it's either InfiniBand or 100 gigabit Ethernet, which has reasonable latencies nowadays, while on the other side it's either 1, 10, or 25 gig Ethernet. Job profile I already said, so large jobs minimize the runtime. On the other side, you don't care how long will the job run, as long as you can submit like tens of thousands of them. Which brings me to what do we have. So Isabella was established in 2002. Actually, before I started working there, I was still studying at that point. So nowadays, it's a typical HPC cluster. So as you can see here in the picture, there's the front end where the people log in. So you only have one publicly available address. They log in here. They use something called batching system or job management system to submit their jobs, which are then executed on a bunch of these worker nodes. We use a parallel file system, which is deployed on 6 bricks. That's called bricks. Basically 6 servers with RAID 6 loans in them. And this is where they store all their data. This is 750 terabytes of storage. Altogether is 16 terabytes of RAM, but as I said, it's a distributed memory model, so you cannot run one process which will address 16 terabytes. It doesn't work that way. You have to use something like MPI or some kind of other distribution over different hosts. Altogether, we have 3,000 CPU cores and 12 GPUs, and my colleague, which is now I see here, was actually giving a speech about those in a different track. Fortunately, it would be much more reasonable if he spoke before me. Anyhow, they are really cool. So we have 140 teraflops, which is give or take 1,000 less than the most powerful machine that we have nowadays. I didn't have time to check what's the least powerful machine on top 500 hit list, but it's probably in a range of 10 times more than we do provide. So, moving on, this is how the usage looks like. So, again, we have resource-hungry users. We provide them 3,000 CPU cores. Unfortunately, in these graphs, you do not see the usage of GPUs, but trust me, it's pretty much the same. So, for really well-used HPC cluster, this thing needs to hit this thing. You cannot achieve it because of the batching system, as I said, so we do not allow users to go straight to the worker nodes. Instead, there's a batching system, and batching system ensures that there's so-called space scheduling. So if you ask for 1 CPU core, you will get that 1 CPU core. There will be no time sharing. If a resource has 28 cores and somebody in the description of their job says, I want to run 28 cores, those 28 cores will be assigned to him. And the next guy who wants 28 cores will basically wait in a queue. So because if we cater for the whole community, we have different kind of jobs. So in some cases, it could be that some of the resources are reserved on the people who are on the top of the list. So there will always be some free slots, but we cannot fill them in because the bigger jobs need to get their slot as well. I will come back to this again. Oh, come on. Now, HTC infrastructure that we have been providing since 2008 is called CRO NGI, which is our national grid infrastructure. It's basically a bunch of smaller clusters which do not have InfiniBand, and they're just connected with the 1 gigabit Ethernet. But in principle, they use the same middleware as the cluster. We just put a little bit more layers in order to enable people to, from a central point, submit jobs to all of these things. So user of this part were basically the same as the other ones. They were just submitting jobs that were more of a HTC in nature, so just using less cores. But however, with this infrastructure, we had several issues, mainly that the grid was not popular anymore, so they discontinued the development of grid middleware. And then there was the aging equipment problem. Normally, HPC lives for 5 years. What you do is you buy something like this, and after 5 years, you just dump it somewhere and put newer and bigger thing. Why? Because you have to remember that these things cost a lot of money because they spend a lot of energy. And with the Moore's law and then the development of new technology, after 5 years, it's generally accepted that these machinery will cost you more than you get the gain from it. They will run way slower than the new generation. So after 5 years, we've actually been to Munich. They just take it, dump it outside, and put the new one in. In our case, we had resources which were 10 years old, which is kind of unacceptable. I will speed up now as I am talking too much. What we did with this thing is as we recognize that the community is pretty much the same, so it's the RBI, the Roger Bošković Institute. There are like 75 resources. These are CPU hours, so when you look at this is usage for 2018. It's when you combine it, this is just for CRO NGI, but when you combine it with Isabella, it will be about 75% of CPU hours were spent by those people up there. The next one is the PMF, so the mathematics and physics and split. They're quite active, but they're more of an HTC user. And then the chemistry is the same people working with the RBI. So what we did, we just took the younger machines and merged them into Isabella. And with CRO NGI, we said, oh, let's do the HTC Cloud Infrastructure. What is HTC Cloud Infrastructure? So we basically have three pillars, which we'll repeat in my future work later on. One is the HPC. On the HPC side, we have Isabella, and we have the Bura, which is the other resource, which is in Rijeka. Unfortunately, not publicly available to all the Croatian researchers as we are. And these resources are used for, as I said, HPC, if you want to run 2,000 cores jobs at the same time and stuff like that. Then you have something called HSC, which is basically infrastructure that enables you to run classic servers, like mail servers, web servers, databases, and stuff like that. On the HSC side, you do not focus on providing a computing power, you focus on providing stable and highly available infrastructure. So basically, we have users that cannot really go there because you do all kinds of overcommitment. If you have a virtualization cluster that was in the previous talk, you do not want to have our users there because they will kill it very quickly. So that's why we came up with the HTC Cloud, which is something in between. So we do not force people to go to batching system and describe their jobs and get their slots and blah, blah, blah. We do not force them to open a full-blown VM that will be highly available and then kill the virtualization and then get kicked out. Instead, we allow them to provide, to deploy their VMs on a new infrastructure. So this will basically cater for those specific cases that cannot fit in the batching system. The advantages of the whole cloud story you already know. So you use a modern system, which are well developed, supported by thousands of users and all kinds of different vendors and blah, blah, blah. And then we already deployed some of these things. I had a speech about this probably 3 or 4 years ago. So just quickly, as I'm running out of time, Ceph, so why we picked Ceph? Because it's kind of a really popular for providing block storage and object storage in combination with the OpenStack. Looking at the usage survey in 2018, they were deployed in 52 countries, and they had over 880 petabytes of storage. Since we collaborate with several sites and high-performance computing centers around Europe and the HTC centers, and it seems that most of the people had the best experience with this thing, so we went for the latest version, of course. You can integrate it with various systems. For us, the Zabbix is interesting because that's our in-house, well, not in-house, that's our solution that we use on SRCE, and then the Puppet as well is interesting. We deployed the new dashboard. It's really cool. I think the Nautilus main functionality that came out was the dashboard. I personally don't like dashboards, but it's pretty cool. You can put it on your slides and stuff. So how does the deployment look like? We have 3 MOM boxes in order to get the high availability thingy, and we have 8 OSD boxes. So this is machinery that we got. Idea is to run 8 OSDs per box. That's why we have 8 cores, 96 gigabyte of RAM, 8 terabyte of HDD. We split the network. We have 4 times 10G. We split the network public-private. We use LATP, so we were able to achieve 18 gigabits a second, which we consider it's nice. We're still in between whether to use the new format BlueStore or FileStore because we do not have any VMEs and our SSDs are too small for the new database thing. It should be 4% of the OSD. With the 8 terabyte of OSDs, we basically can have 2 databases on the SSDs and 6 of them without databases. So we're now trying to we're considering whether to go for the file store and put the log on the SSDs or transform the SSDs in the pool for itself. So this is something which is still ongoing. And then the OpenStack, of course. Why? Again, the same story. Most of the people seem to be using that, and we can gather knowledge from our colleagues abroad. However, I would like to emphasize that our goal is not to provide a full-blown OpenStack solution here. We basically try to cater for our needs. So we do not need fancy stuff like virtual DC or SDN. What we need is basically, we need to be able to provision VMs, which will function in a similar manner as the worker nodes in the HPC cluster. So for that part, we now have 25 compute nodes, which they give us 600 CPU cores. So that's like 5 times less than we have in Isabella. Again, they have 2 times 10 gigabits in LATs, which works nice. Each box has 192 gigs. And we did the measurement, well, actually a colleague did the measurement, and we got 4.8 gigaflops. So without InfiniBand and with these particular CPUs, which are not for HPC usage, the new generation, the ROM that will come out in summer will be more HPC friendly. This thing is more for these HTC cloud usage. So 4.8 versus 140 is a bit smaller. We do not have stretch on compute nodes. All the storage for VMs will be provided from the Ceph pool. This is how it looks like. Unfortunately, in the last moment, I didn't find a picture. Our networking team did a really good job of connecting all this stuff on the other side. But however, if you're close to our computing center, you might as well stop by and I will show it to you. So, I'm really coming to the end of my time. What are the use cases to be concrete? So, on the HPC cluster, the batching is a problem for people who have applications that need interaction. We just cannot provide it for them because we do not have enough resources. I could show you the graphs where you see that most of people need to wait for at least a day or 2 for their job to start running. Starting an interactive graphic application, it just does not compute on the HPC. That's why this thing will work for them. Another use case is enabling people to deploy their own HPC clusters. So this is something which sounds cool, but we are still considering whether it's easier to just deploy, look at the usage of the cloud, and if it's underutilized, we just connect some of the nodes into existing clusters and just put them in a separate queue and enable people to run their stuff as they run it normally. Then the data analysis systems, this is something that we really lack, and there's more and more requests for this thing, so we kind of hope this will solve it by using the OpenStack Sahara. We already have interesting people from this particular university, faculty, sorry. And then the portals for specific applications, so like R, you can provide an R Studio, which can in the backend connect to the Apache Spark. So this is something that colleagues from the RBI are doing, so we're kind of collaborating with them on how this thing, the whole this thing will work. And then in the end, there's the EGI Fed Cloud, which is the big grid infrastructure. This is interesting for people who are participating in a big European scientific projects. So they will go through this thing. Now, finally, issues. So the biggest issue is that we have a traditional user which is accustomed to two things. One is the job management system. So they do not understand what the VM is, what the cloud is, what the network is. They do not care about any of that. They just want to analyze their molecules, their genomes, or whatever else. And then the second thing is they do not often, there are bright exceptions, but most often we optimize and deploy applications for them. So since we have different kind of worker nodes, we needed actually to optimize applications on them to work properly. So all this will be a problem when we try to transition them to the HTC Cloud. Then there's the direct access to VMs, which is even worse because you have the maintenance overhead. If they run something which is publicly available for a month, who is going to make sure that this thing is properly patched, maintained, and so forth? Then there's a problem with high availability, but that comes in a description of our service, so that's not really a problem. Then the VM usage. The biggest problem is that our people, whenever they come along and say, I need to do some really heavy calculation. Okay, what do you need to calculate? How many resources do you need? All of them. So we need to come up with a really cool quotas, because the batching system is nice, because it just lets people go into the resources when the resources are available. But with the OpenStack Cloud, they will ask for the VM, then they will get the VM, and they might not use it, so it might just not be utilized for months there. So we need to figure out how to monitor that and explain them this resource quotas, which work perfectly fine. Okay, I'm done. For the future work, we need to resolve all these issues. And then there's the big infrastructure project, which we are now building. It's an EU-funded project that started last year. The idea is to build modern data centers on 5 sites, so 5 universities. I know we have more of them, so I'm not ignoring any of the other ones. We're going to provide 1.2 petaflops of HPC resources there with 2 petabytes of high-performance storage, 4 petabytes for HTC, 20,000 CPU cores, which will be distributed on several. So there are, of course, GPUs included in this picture. HSC infrastructure, 10 petabytes of storage. And the most important part, we're planning to buy some of the software stuff for people and provide support in form of 5 e-scientists, I think. So to conclude, cloud is promising for my area, our area, but it has some issues that we need to resolve. However, it's really needed in order to cater to all of the scientific needs. Thank you for your attention. Questions?